Hello all. In this video, we're going to take a closer look at Numpy arrays. We've already talked about the fact that images, when we read them in with OpenCV, they are represented as Numpy arrays. So you should already be remembering that Numpy arrays for a color image, they have a width and a height, which are the grid of pixels, and then they have a third dimension, which is the channel dimension. So they have blue, green, and red channels in that third dimension. So that's our starting point. What we're going to do is to look at some of the tools that Numpy provides to us to let us manipulate images and to do various other things with data that is not an image data, potentially. All right, so we're going to take a look at my notes. We're going to start with Numpy operations. Now, the first thing we're actually going to do is to look a bit closer at data types again. So we've already talked about number types in Python, but number types in Python are actually rather high level. And it's worth understanding that in a lot of programming languages and in the computer down deep in the depths, there are actually a lot of different representations of numbers, both of integers and of floating point numbers, and Python kind of hides that from us. So there's an integer data type in Python, but any integer of any size is all just called an int. And in fact, in Python, you can make integers of ridiculously large sizes that are not supported by the hardware of the computer, and that in other programming languages you would not be able to represent exactly. So that's all good for us as Python programmers, but there are times when we need to know specifics about exactly how our numbers are represented. Numpy gives us that control in Python. It implements additional number types that are like the types you would see in a language such as C or C++ or Java. All right, so fixed length numbers is the way I want you to think about this. The hardware of the computer implements integers of specific lengths. And the typical lengths inside a typical modern computer would be an 8-bit long integer, which we've talked a little bit about before, a 16-bit long integer, 32 bits long, or 64 bits. So if you have 64 bits, you can represent numbers, you can represent 2 to the 64th different numbers. And so if those are positive and negative, then you have about half of those are positive and half are negative. Or if you have all positive numbers or non-negative numbers, then you can represent the whole 2 to the 64th different possible integer values. Floating point numbers have either 32 bits or 64 bits. So they're also on the large end, but they have two different representations as well. Now, I made a distinction just a moment ago between integers that include negative numbers and integers that don't. That's because they are actually different types deep down inside the computer. We have unsigned integers, which is basically non-negative. 0 and above are considered unsigned because you don't have to put a sign on them. There's no such thing as a negative number in that realm. And then as an alternative, we also have signed integers, which are negative and positive, but they still fit within these four sizes. So if we have a 16-bit integer, it could be unsigned and represent only positive values, or we could be using those 16 bits to represent positive and negative. All right, in Numpy, we have a standard set of types that Numpy has defined for us. These correspond to types you would see in other programming languages. So you can see I've made sort of three categories: signed integers, unsigned integers, and floating point. And then I also have in the other dimension the size, the number of bits that are assigned to that particular type. So int 8 represents numbers that use 8 bits, and they are both positive and negative. And this runs more or less from, say, negative 127 up to positive 126 or something like that. It's about half as large as if we have unsigned ints, because half of the values are given to negatives and half to positives. So for unsigned integers that are 8 bits long, it's uint 8. Those are the ones we've been using for color values. They are from 0 to 255. Both of these, if they're 8 bits long, they have 256 different binary patterns. It's just whether you interpret some of those patterns as negative numbers or not that makes the difference in how these two are treated. If you have 16 bits, that means you have 2 to the 16th different patterns. You can work out what that is. It's pretty big. And we have, again, int 16 and uint 16. And similarly for 32 and 64-bit numbers. And then we also can distinguish the floating point numbers at that size as well. So when you create an array in Numpy, if it's an array of numbers, Numpy wants to know which of these types you want it to have. And the reason is how Numpy arrays are actually implemented. So I have some notes here about arrays in Numpy. They are similar to vectors and matrices in mathematics. They are similar to arrays in other programming languages. If so, C or C++, they have arrays of a particular type. So you'd have an array of integers or an array of floating point numbers. And they would probably also be specifying which size of integer or floating point number you are using. So it's very similar to that kind of an implementation, which we don't have with lists in Python. Lists are a different kind of data structure than an array. It has some great benefits, but also some downsides. And for our purposes, we really do want true arrays to represent images, because it's a lot of data and we do a whole lot of matrix kind of operations on it. So what's specific about an array? It is implemented way down deep in the computer's memory. An array sits in a contiguous block of memory. It's a set of memory that's all one big box, and all of the data is in there, one number after another. So if you were reading the memory of the computer and you knew that these were 8-bit numbers, you would count 1, 2, 3, 4, 5, 6, 7, 8. That's the first number, and the very next bit inside the computer is the start of the next number. That's what I mean by contiguous. They are all right together. There are no gaps. They're not spread out in memory at all. This has a lot of benefits for us, because it means that if we know the index of a particular value in the array, we can calculate exactly. Well, we have to know the index of a particular value in the array, and we have to know the starting point for this block of memory where the array is sitting. And if we have those two things, then we can go calculate exactly the memory location where that other data is, and we can go and find it. It's extremely efficient for looking up or storing data into this array structure. We also can implement extremely efficient operations that parallelize this kind of data. So this kind of data can be run on GPUs if we have access to it, and at the very least, it's extremely easy to parallelize when you have this kind of data. So arrays in Numpy typically hold just one kind of data, and that data is one of those types that I listed above. And they typically have a fixed size. You cannot change the size of an array once you create it. You can recreate a bigger array, but it's fixed in size. This is different than what we were just learning recently about lists. Lists are variable in size. You can add and remove data from lists dynamically, and that makes them fundamentally a different kind of data type than an array. You tell it when you want an array, you say how big you want it to be, and then it will make that much space, allocate that much space in memory for it, and that's as much as you've got. If you need more, you have to start over making a whole new larger array. There are two things that are highlighted right here in purple. That's the shape and the D type. These are two attributes that arrays in Numpy have. Shape will tell you the dimension. So if you ask about the shape, you get a tuple, and it tells you exactly how tall, how wide, how deep, however many dimensions you have. You could have 4, 5, 6, 7 dimensions if you want to. It'll tell you exactly how large the array is in each of the dimensions that it has. All right, so just to remind you again briefly, images as NumPy arrays. Color images are three-dimensional. They have height, they have width, that makes a grid, and they have depth because they have three different numbers to represent each color, blue, green, and red in the case of OpenCV. Grayscale images are two-dimensional arrays. They have height and width, and inside that grid you store just the brightness value. Because gray happens when blue, green, and red values are equal. So a grayscale image only needs one number per each grid pixel. Normally we use uint8 for pixel and channel values. You can use other things. It's just functions like imshow are not going to work with them well. They're expecting a certain type of data, and you'll run into that with some other OpenCV operations as well. All right, I just wanted this code snippet just to note, if you take the code from, this is from my notes document, you can copy it. In fact, very often it has a little copy icon on it. It doesn't seem to have it here. But you can copy this code and run it. What this code is doing is reading into very differently sized arrays or images. And in the case of the second one, which is a very large image, it's then calling a function in OpenCV. CVT is short for convert. Convert color is the name of this function. And it basically, you give it a code at the end which tells you what conversion you want. We are saying here BGR to gray. That means convert this from a regular BGR color image to be a grayscale image. So image 3 will be a grayscale version of image 2. All right, the other thing that I'm doing here is just printing the shapes and the data types so that you can see what they look like. And I encourage you to actually run this on your own and see what happens. Next, we're going to talk about NumPy functions. There are so many functions in NumPy. We are not talking about even a tiny fraction of them. Many of the things that we will do with OpenCV, theoretically you could do with NumPy. They're just often a little awkward, as you'll see when we get into the image arithmetic section in a future video. So we have a set of functions here that are the ones that are focused on in the reading that goes along with this. np.array is a really useful function. We'll use it quite often. You can give it a list that has a particular structure of rows and columns represented as lists within lists, and it will convert that into an array with the same dimensions. And you can tell it what data type you want, or it will use a data type, a default data type if you don't. As array is also a similar function. It doesn't always copy the data. If you give it an array and you ask it, say, as array, sometimes it keeps the same data just to save memory. As type is a method that will allow you to take an array and produce an array of a different type. So if I have uint8 is the data type for a given array, but I actually need to turn those into floating point numbers, you can use as type to tell it, I would like to convert this to this other data type. And there are other operations to do that as well. There is, in fact, a function called float32, which, much like our int function and float function, will convert between integer and floating types. There are functions in NumPy that will just do that conversion for you as well. We focused in the past, and actually we will continue focusing for the most part on these next two functions that are listed here, zeros and ones. Zeros and ones build arrays from scratch. So you tell it the size you want. Remember I said you always have to tell how big an array is at the point that you're creating an array, because it needs to find a contiguous block of memory for that array to sit in. So we tell it the size, the dimensions we want our array to have, and what type of data, and it builds a new array and fills it with zeros. This is really handy for us because from our perspective, if we make it look like an image in its dimensions, then it treats it as a black image. That is a good starting point for doing other things. The ones function works very similarly, but it fills the array with ones. This is great for a lot of mathematical applications. In our case, if you fill it all with ones, 1 is really close to 0 when you think of our spread from 0 to 255. So if you display it, it doesn't look that much different. But you could do things like multiply by 128, and then it would be a nice middle gray image. And it also otherwise is just a good building block for then doing additional things. We haven't talked as much about these other two functions. They were mentioned in the reading, but we're not going to spend as much time on them. I might have an example or two that I can talk through down below. A-range is kind of handy. It's like an array version of the built-in range function that we've been using with for loops all along. A-range, you give it a starting value, an ending value, and a step size, and it builds an array with those values. So it'll go from the starting value up to, but not including the ending value, increasing each time by the certain step size. But it builds it as an array. And it works on non-integers. So if I want to have, let's say, from 0 to 10, but I want to go up in increments of 0.25, I can do that with A-range. I can say start at 0, go up to 10, increase by 0.25 each time, and it would go 0, 0.25, 0.5, 0.75, 1, 1.25, and so on. So it's really handy if you need that kind of thing. We aren't going to use that much with images, but it is there. And random.rand, you tell it, again, the size you want and the data type, and it makes an array of that size, just like zeros and ones, except it fills it with random values. So you can specify the range that you want those values to be. So you could say, I want a 10 by 10 array, and I fill it with random numbers between 1 and 100. And it will do that for you. All right, as I said, we will use array a lot. We might use as type once in a while. We will use zeros and ones as we already have. And the rest of these are just useful in case you never need them. All right, I have a point here that's actually really important. If you've ever programmed before and you've done things with, say, two-dimensional arrays, oftentimes what you do in your code is you end up writing nested for loops. So you have one for loop that is looping over the rows of a given array, and then inside that, for each row value, you have another for loop that happens that iterates over the columns of the array. This is a really good way to go through and touch every value in an array. But the fact is that for our purposes, we want to do that as little as possible. We would like instead to kind of take, this is a linear algebra kind of an approach. We want to treat arrays as a block and operate on the whole block as a whole. This allows us to use algorithms, we don't have to know about them, but they're implemented in Numpy, that are highly optimized for doing these operations as quickly as possible. And I guarantee that your code will run slower if you iterate over all of the row and column values and change every value in the array that way versus using NumPy's arithmetic tools to do it for you. So I have an example here. I think I'm going to switch over and look at arithmetic. So this is basic arithmetic on arrays. I'm going to look at some examples in Python in our PyCharm editor that I have been using, just so that we can actually run them and see what happens. And I encourage you again to take these examples and try them out for yourself. All right, so here we have an example. I have created here two arrays, and let's just start off by looking at their attributes. So I'm going to print array 1's shape and array 1's data type, and I'm actually going to label this R1 with a little string, and I'll do the same thing for R2, R2.shape, R2.dtype, just so we can actually be sure that these are doing what we want. Okay, so array 1 is 3 by 3, and it's 64-bit integers, which is the default. I did not specify a data type here, so it used 64-bit integers, and that means positives and negatives. So all of these are represented exactly. And array 2 is also 3 by 3. I made these two to be the same size on purpose because that makes it easier to do arithmetic with them. All right, so I said, well, suppose that we want to do something with these two arrays. We want to combine them in some way. The arithmetic operations do what is called element-wise operations. So if I say add array 1 and array 2, R1 and R2, what that will do is pair up corresponding positions. And you can't do that unless they're the same shape. There's some ways in which that can be extended. The reading goes into that, but fundamentally just make them the same shape. Just while you're learning all about this. So up here we have a value at position 0, 0. We would look at the 0, 0 position down here. If we're adding the arrays together, we would add those elements, 1 and 6. And that would be the new value that would go in the corresponding position in our answer array. And we do the same thing across the line. 5 plus 2, 4 plus 3. The next row, 4 plus -1, 5 plus -2, and so forth. So let's just take a look at what happens when I do that. So new array equals R1 plus R2. And then we'll just print it and see what it shows. All right, so if you look at this, it should make sense how it worked out. I added 10 to the ones up here, so the bottom row was 17, 18, 19. In the middle, they were kind of counterbalancing each other, so we ended up 3, 3, 3, and the top was 7, 7, 7. So it just added up the corresponding elements and gave us a new array with the result. We can subtract arrays from each other. I'm going to do array 2 minus array 1 because for whatever reason, most of array 2 is bigger than most of array 1. And so we would get 6 minus 1, 5 minus 2, 4 minus 3, and so forth. And you can see how that works out. So these operations are provided by the Numpy module, and they allow us to do this work at the level of the whole array. We can do other things as well, so we don't have to have two arrays. I could say 10 times R1, and I guess I should keep printing it. So here I have the multiplication operator. It has an array on one side, and on the other side it has a number, just a plain number. What that will do is it will apply this number and that operation to each value in the array. So it should multiply every value in the array by 10. And you can see that it does. This is the fundamentals of what's happening here. We can do this kind of arithmetic on NumPy arrays, and that also includes images because images are NumPy arrays, right? So we can, in fact, add a constant to an image or add two images together and get a new image as the result. We're going to look at that in a later video. All right, there are two other ideas that are important that I want to talk about. I'm going to switch back to my notes so we can talk about them. The most important of these remaining is slicing on arrays. So we learned about slicing in the context of lists and strings, where we can use it to pull out a section of a string or a section of a list, some selection of values from the list or characters from the string. We can also use slicing on arrays, and NumPy implements an extension of the notation that turns out to be very handy. So what we can do when we're slicing with arrays, we give the name of the array and we have the square brackets. I'll show you too, you can actually use selection with arrays as well, and I'll do some examples in a moment. But for each dimension that the array has, you can use the colon notation as we've learned it so far, for each dimension. So in this case, this would say start with the dimension at index 1 and go up to but not including the dimension at index 2. So that's going to be only one row of the array. And the other one says start at 1 and go up to 3, so it will give you two rows, two columns of the array. So it can select out a subsection of the original array. This array was in my notes. Where is it defined? A1. It's got two rows and four columns in each row. 1, 2, 3, 4, 2, 3, 4, 5. And what you can see is we got the second row, but only the 3, 4 values were selected, position 1 and position 2 of the second row of this A1 array. All right, I have some other weirdness here. I'm going to come back to that. Let's go and look at some examples and just try a few things with these arrays. So what I want to do is to show you some ways that you can access arrays as well. So I can, I'm just going to print a couple of things. So let's do array 1 sub 2. And then we'll print array 2 sub 0. And we'll just take a look at those. So there I'm just giving it one number. And what that will do is select the row that I've told it to select. So if I put one number in here, that's the row index. It's giving me the 7, 8, 9 because they're 0, 1, 2 are the indices for the rows. And here we're getting the 0th row, which is the 6, 5, 4 of the second array. So we can do that with just a single index. It'll give us a whole row. What if I wanted an actual specific value? So I want to get the 5 out of array 1. Well, the 5 is in row 1, so I'd specify that first. And then I can do comma and give the index in columns, the column index, which is also 1. And then I could do the same thing here. I could say 0 sub comma 2. That will look in the 0th row, but it'll give me the one that's at column index 2. So that should be the 4. Let's run it again. And yes, we get the 5 for the one and we get the 4 for the other. This can be extended into multiple additional dimensions if your array has them. All right, so that's individual numbers, but we were talking about slicing. So suppose that instead of wanting the 5, I want, say, 2 and 5. Then what I want to do is, here where I specified 1 as the row index I was interested in, I'd want to say, oh, well, I want row 0 and row 1 and not row 2. So I would say 0 colon 2 and then say I want the 1 value. And that should pull out the 2 and the 5. I could do the same thing here. I could say I want the 0 row, but then I want columns 0 colon 2, and that should give me a subsection of that one as well. So here you can see where I said 0 colon 2 comma 1, it's given me 2, 5. Notice that it just turned that into a nice little vector by itself. So it's not in the same structure as it had been. It's just the 2 and the 5 together. These are printing as if they look maybe like lists, but notice there's no comma when you print, and that's an indication these are still Numpy arrays. If you actually look at them, the type is still an ND array. And the 6 and 5 I was able to pull out as well. If I wanted a whole column, so maybe in array 2, I want that last column, what I can do is use the colon with nothing before or after it, which says start at the beginning row, go all the way to the last row, and then in the second dimension, after the comma, I tell it which columns I want, and I could say 2 there. And that will give me all the rows, but only the 2 column. So it gives me the 4, the -3, and the 10. This operation, this slicing and accessing with square brackets, allows us to really dynamically grab any subset of the values from the array, no matter how many dimensions there are. It's extremely useful. And it turns out to be useful with images as well. As we will see in a later video, we can pull out a subsection of the image. We could access a whole channel of the image. Pretty much anything you want to do, these slicing operators can do. All right, the last topic, I'm just really going to mention it here. I'm not even going to do examples of it because it isn't something we're going to use a lot, although it is powerful and I think awfully fun once you understand what it's doing. We might run across this one or two places as we go forward, but it's not super critical. It's just you should know it's a possibility. So in NumPy, we can ask Boolean expressions that include an array. And when we do that, what we get back is, again, an element-wise operation. So if I say A2 greater than 3, I should do one of these in Python. I'm going to switch over and do that. We can do things like greater than, less than, equal to, not equal to, and what we get back is an array holding the trues and falses for that operation happening across the entire array. So let's go back to PyCharm, and I'll just do an example really quickly. All right, so suppose I have our two arrays that we've been looking at all along. And I am just going to say B1 is array 1 greater than 6, and B2 is array 2 less than or equal to 5. And then we'll print them. I think I'm going to print them one at a time so we can talk about them. So we'll just run this and take a look at what the result looks like. So we had our array 1. It does it element-wise. So this says greater than 6. It says, is this value greater than 6? Is this value greater than 6? Is this value greater than 6? And the results go into the array. So which values are greater than 6? Well, the last one in the second row and then the third row. So if you look, 6 is not greater than 6. It's only the third row. So if you look at the output, we get all falses for the first two rows, and then we get true, true, true because the last three values are greater than 6. If we were to print B2, we said is in array 2, is each value less than or equal to 5? And it will show us that yes, the second and third values are less than or equal to 5, the entire middle row, and nothing in the third row. You can also do more complex comparisons like comparing array 1 to array 2. And this will just apply this operation to corresponding values, just like the arithmetic operations we were looking at before. So it says false here. That's because it said, is 1 greater than 6? No. Is 2 greater than 5? Is 3 greater than 4? Is 4 greater than -1? Yes. Is 5 greater than -2? Yes, and so on. So these arrays are useful if you are looking for particular values. You can also do a count of how many falses and trues there are in the array. You can actually also use these Boolean arrays as a substitute form of indexing, and it will extract just the values where there were trues. So this is like the deep, cool use of this. So I'm going to try this on the fly. So what I do is I put that Boolean array into the square brackets instead of indices, and what I should get back, yes, is just the values where there was a true. So there was true, true, true across the middle, and I got back the -1, -2, -3. I'm going to try a slightly different question. Let's try it with less than or equal. I want a few more trues, so they're not all coming from one column. True, 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 false, 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 true, true, true. What you can see, what I wanted to show, is that it basically collects up all the values where there were trues, and it just makes one big long vector of them. So it's a way of selecting values out of an array as well with these little Boolean arrays. They are very handy. I don't know how frequently we'll use them, but I think they're kind of cool, and everybody should know that they exist. All right, so this has been a really, really rapid overview of some of the things that you can do with NumPy. It is a gigantic library. It has so many operations. It has really good documentation, but you do have to learn how to read it. So I encourage you to start looking at the NumPy documentation so that you can learn how to make sense out of what it's telling you. These will become more important later on, especially when we start talking about machine learning, because a lot of work in machine learning is done with NumPy arrays. And so they're a very, very handy tool to understand. For now, we'll use them sometimes to do some things that we want to do with images, and so it's just good to have a sense of this smaller subset of commands. I'm going to stop there. We'll talk about image arithmetic in the next video, and I will see you there very soon.